Good day, students. So welcome to number 4 on our review of the AP Calc exam for 2014. In this installment, we're going to be addressing concepts such as position or distance, velocity, acceleration, and related rates. For the remainder of this review series, you can go to mathgodser.com under AP Calculus. So let's go ahead and take a look at the first part of question 4. So let me just read the question. It says, trains A runs back and forth on an east-west section of railroad track. Train A's velocity measured in meters per minute is given by a differentiable function, velocity of A of t, where t is measured in minutes. Selected values for v of A of t are given in the table above. So part A, we had to find the average acceleration of train A from 2 to 8. So one thing I like to do real quick is do a real quick review on two formulas that are often confused with each other, which are the average rate of change formula and the average value. So the average value of a function, f average. Let's say you want to calculate f average on an interval AB. The average value of a function is given by the notation 1 over b minus a times the integral from a to b of f of x dx. Alright, this is the average of a function or the average value of a function. Just like this question is asking for the average value of the acceleration. You also have the average rate of change, let me call it ROC, of a function on an interval AB. The average rate of change is simply f of b minus f of a divided by b minus a. Alright? These two are connected. In what way? Well, let's take a look at this average rate of change for a second. This average rate of change can be written as 1 over b minus a times the integral from a to b of the derivative of f, which is f prime of x dx. Okay? So then, by using the average value formula, this can further be expressed as the average value of the derivative of a function from a to b. Okay, so what's the connection here? The average rate of change is basically the average value of the derivative of that function. That's what this connection here shows. All right? So how does this relate to the problem that we're about to do? So if you think about the connection between the velocity and the acceleration, the derivative of velocity is acceleration, right? So if you're looking for the average acceleration, you're basically looking for the average rate of change of the velocity on that interval. All right, so what am I saying? Let me just show it to you real quick. So let's say you're looking for the average ROC of v of t on an interval AB. Okay, that's going to simply be v of b minus v of a over b minus a. Okay, average rate of change is like the slope of the secant line, right, on an interval, closed interval AB. This is the same thing as 1 over b minus a times the definite integral from a to b of the derivative of v, right? V prime of x dx. But what is the derivative of velocity? The derivative of velocity is acceleration, so it's 1 over b minus a of the integral from a to b of a of x dx. Take a moment and look at this formula closely. What formula is this? This is the formula for the average value of the acceleration. Okay, so a average. This is the formula for a average from a to b. And this is exactly what the problem is asking you to find. The problem is asking you to find the average acceleration of the train from 2 to 8. This is A and this is B right here, okay? So let's go ahead and do the problem. So for part A, we're looking for A average. A average from where we're going from. We're going from 2 all the way to 8. Let me make use of variables first to get the simplified form of the formula I'm going to be using. Then I'll input my A and B values, okay? So average value of the average value of the acceleration from A to B is given by 1 over B minus A times the integral from A to B of A of t dt. Alright, so when you apply FTC part 1 to this integral right here, you have 1 over B minus A times the antiderivative of acceleration is velocity evaluated at the upper limit minus the velocity evaluated at the lower limit, like that. And then that becomes V of B minus V of A over B minus A. This just highlights what I stated earlier, that the average rate of change of the velocity is equal to the average value of the acceleration. Alright, so this is the formula we're using. Now let's apply this formula to this particular problem. So the acceleration, the average acceleration, not rate of change, the average value of the acceleration from 2 to 8, going to include 8, is equal to velocity evaluated at 8 minus the velocity evaluated at 2 divided by 8 minus 2. Okay, so here you just basically use a table to figure out what V of 8 is and V of 2. So V of 8 is negative 120, V of 2 is 100. You guys are going to input those values into your formula here. So negative 120 minus positive 100 divided by 8 minus 2. And when you do the calculations, you get negative 110 over 3 meters per minute square. Alright, so there goes your average acceleration from 2 to 8 using the table. Alright, let's take a look at part B. It says, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t with 5 less than t, t is less than 8? Give a reason for your answer. So we're talking about an output value that should be somewhere between two values on the table, namely between 5 and 8. So when you're looking for continuity, the existence of an output within an interval, the concept or theorem you want to think of is the intermediate value theorem. When you're looking for the existence of a derivative, the slope of a tangent line somewhere within an interval, then you think about the mean value theorem. Rose value theorem if the derivative is 0. Okay, we're not talking about existence of derivatives on an interval. We're talking about the outputs, the existence of a particular output on an interval. So we're going to be thinking about the intermediate value theorem here. So what is the IVT again? Let's just review that of the intermediate value theorem real quick, and then we can see if it's applicable to this situation. So for IVT, intermediate value theorem, if f is continuous, on an interval AB, a closed interval AB, continuous in AB, and f of A is less than or equal to f of B, then there exists a C in that closed interval AB, such that f of A is less than or equal to f of C, and f of C is less than or equal to f of B. Okay, so this is applicable when you have a continuous function on a bounded interval. Okay, so in this situation, we know that negative 100 is really in between the two extreme values. Let me show you what those boundary values are. So if you look at the table, this is 40 for 5, and then negative 120 for 8. So negative 110 is clearly inside this interval. So has to be C between 5 and 8 where the output value is going to be negative 110. All right, so let's go ahead and apply that here. So the question asks if the table supports the conclusion that there is a t where the velocity is negative 100. Our answer is yes. Let's change the color. That answer is yes. And the reason is by the intermediate value theorem. Let's write it out. By the intermediate value theorem. By the intermediate value theorem, there exists, let's see, in this case we'll call it a time t in that interval. There exists a time t in this interval, 5 less than t is an 8, where f of t is equal to negative, not f of t, v of t, because we're looking at the velocity function here, where v of t is equal to negative 100. Why? Since v of t, a velocity function, think about it, is a continuous function, right? In this situation, it's a continuous function. Since the v of t is continuous, it's continuous on that interval 5, 8, and v of v of 5, v of 8 is less than v of 5. It's kind of reversed here, v of 5. Okay, so if the velocity function is continuous on this interval, and you have this ordering situation here where v of 8 is less than v of 5, then this implies that there is a t where what? V of 8 is less than or equal to v of t, kind of running out of space here, and that's less than or equal to v of 5. Okay, let me rewrite it here so you can clearly see. So where v of 8 is less than or equal to v of t, and that's less than or equal to v of 5, like that. So that's basically the conclusion. Okay, just another quick point to note is this t has to be it has to be in the interval 5 to 8. Okay, that t has to be in that interval between 5 and 8 where this conclusion is met. All right, let's take a look at part C. It says at time t equals 2, train's A position is 300 meters east of the origin station, and the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time 12 minutes. Okay, use a trapezoidal sum with 3 sub intervals indicated by the table to approximate the position of the train at t equals 12. Alright, so if you think about position and velocity, position is the antiderivative of velocity. So let's go ahead and write down some formulas real quick. So let's write down a formula. So we know that if we carry out the integral of the velocity function from a to b, so integral from a to b of the velocity v of t dt, that's going to give us the position, because the antiderivative of velocity is position, right? It's going to give us the position evaluated at b minus the position evaluated at a, using FTC part 1. So this simply follows that the position at b is what you get when you add the position at a to both sides. So it's s of a plus the integral from a to b of v of t dt. You can think about s of a as a c that you add on when you find the antiderivative, okay? Alright, so in this problem, we're going from 2 all the way to 12. So what we're going to be looking for is the s of 12, where b is basically 12 and a is 2. Okay, so let's go ahead and apply to this situation. Part C, we're looking for the position at 12, and that's going to be the position at 2 minus the integral from where to where. Remember, we're going from 2 all the way to 12. Okay, a is 2 and b is 12. So the integral from 2 to 12 of your velocity function, t. Okay, so this is what we're using to find the position at t equals 12. Now we do not have a velocity function, we have a table, so we want to use the trapezoidal approximation to approximate what the value of this integral is. It's supposed to be a plus. Sorry about that. Alright, so what's the value of this integral? That's what we're approximating with a trapezoidal approximation. Okay? So let's go ahead and do that. S of 12 is going to be S of 2 using the table, the output, the position when the time is 2. What was the position when time is 2? You're told here that it's 300 meters. Okay, so keep that in mind. Position when time is 2 is 300. And then we're going to approximate this using a trapezoidal approximation. Let's not do that yet. So 12 dft dt. So how do we approximate v of t dt, this definite integral right here? How do we do that? Before we use our trapezoidal sum to find the approximation of that definite integral, let's review our formulas real quick for the trapezoidal sum. Alright, so the trapezoidal formula again. So there are two cases. One case involves uniform widths. If your intervals are uniform, then you're going to use this approximation. T is approximately 1/2 times the uniform width, right? You multiply that by y1 plus 2y2 plus, and the pattern goes on, all the way to the end. So plus dot 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 plus 2 y sub n minus 1 plus y sub n. Okay, this is when you have uniform widths. You gotta be really careful here. Uniform widths. Now, when the widths are not uniform, in that case, you have to calculate the areas of each trapezoid independently. Okay, so in that case, let's call this case 1. In case 2, it's hard. Okay, Case 2, you're going to have to do more work. The only thing you can factor out is the 1/2, all right? And then you're going to have the area of the first, well, double the area of the first trapezoid, which is y1 plus y2, that multiplied by the width of the first trapezoid, okay? Plus this next one, next trapezoid, y2 plus y3 over, no, over. We already factored out 1/2, so no need for that, times w2. And then the pattern goes on and on and on until you end up with yn minus 1 plus yn times the width of the n minus 1 trapezoid. Okay, so this is very easy. This one involves more work. So what's applicable to this situation right here? Okay, so we're going to have to take a detour to find what the value of this integral. So we want to approximate the integral from 2 to 12 using the table. So what I always like to do is I like to start with a partition. So let's see let's do it this way. We have 2 to 12. Let me draw it to scale to some extent so you can really see what's going on here. So you have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, just to illustrate the non-uniform widths visually for you, you can just subtract the numbers to see that they're not uniform. All right, so that goes my time interval from 2 all the way to 12. All right, let's go ahead and break it up. So we have, let's see, we have 2, 3, 4, 5. We have 5. And then the next is 8, 6, 7, 8. And then the next is what? 12. 1, 2, 3, 4. All right, so this is T1, T1, T2, T3, T4. What do you notice? This is width 1 right here. Width 1 is 3 units long, so this is width 1. Width 1 is 3. Okay, good. And then width number 2 is also 3. And then lastly, width number 3 is 4 units. So what do we do here? We're going to have to use the second formula since all the widths are not the same. Okay? So let's go ahead and set that up. You just want to note that y1 is equal to v of t1, right? y1 is equal to v of t1. So you're basically using your table. So v of t1 is v of 2. That's what you get when you plug 2 in, and that's 100. And then y2, if you look at your table, same thing as v of 5, which is 40. And then y3, let me just put that here, v of t2. And then y3 is what you get when you evaluate the velocity at t3. That's v of 8. V of 8 is negative 120. And then y4, v of t4, which is v of 12, which is negative 150. You don't have to do this. I'm just trying to show you how everything is connected. I'm just doing extras here so you can really understand what's going on. So now we have everything we need. So let's go ahead and approximate what the value of the definite integral is. So we have the integral from 2 to 12 of v of t dt is approximately what you get when you calculate, let's take out the 1/2, and then we're just going to apply this formula right here to this situation. So we have y1 plus y2. y1 plus y2 is 100 plus 4 multiplied by width 1, which is 3, plus y2 plus y3, which is 40 plus negative 120, which is 40 minus 120, times the width of the times W2. Okay, W2 is 3, and then plus we have done y1, y2, y2, y3. The last one is going to be y3, y4. Okay, so y3, y4 is going to be negative 120 plus negative 150. So you have plus plus, so plus plus is minus. Plus plus is minus. Minus 150. I mean, plus minus is minus. And then the width is 4, like that. All right, so that's the value of the expression uh, for the approximation of the value of the integral. Okay, hopefully you didn't get confused with this formula. What I did, let me just put it on the side here so you're clear. What I did here for the integral from a to b of v of t dt, I just approximated it by saying, oh, since we have 3 subintervals, we're going to do 1/2 times y1 plus y2 multiplied by w1 plus y2 plus y3 multiplied by w2 plus y2 y3 plus y4 multiplied by w3. Okay, I just took this formula basically and I added one more term to it. So that's how I got this right here. Okay, and then when you do the calculations in your calculator, you end up with negative 150. Well, this is without adding the other piece to it. Negative, actually 450, negative 450. All right, so remember we also still have to add this 300 right there to finish up the whole problem. So S, the position at t equals 12 minutes is approximately 300 plus negative 450. And your final answer is going to be negative 150 meters. All right, let's move on to the last part. All right, so for part D, it says the second train B travels north from the origin station at time t. The velocity of B is given by the velocity function, negative 5t squared plus 60t plus 25, and at time t equals 2, the train is 400 meters north of the station. Find the rate in meters per second at which the distance between train A and B is changing at time t equals 2. So this is a related rates problem. Let's see if we can generate a formula that relates the distances between the two trains. Remember that the other train A, is going east to west, and train B is going north to south. All right. So if we just want to take a snapshot of the situation, we have a train heading north and another train going east and west. So let's say at t equals 2, I don't know exactly where the train is. Let's say the train is, well, actually, at t equals 2, it tells us it's 300 meters, so we actually know. Because in part C, if you go back to part C, it says at time t equals 2, the train's A's position was 300, so we actually know what that is. Okay, so let's say this is the direction of train A, and this is the direction of train B. 300, let's say somewhere here. That's the position of train A, and then the position of train B is 400. You're told here 1, 2, 3, 4. This is a multiple of the, well, I'll tell you in a minute. So the distance between them is basically the hypotenuse of this right triangle here. Okay, so using your 3, 4, 5 triangle, this is 300. This is 400, and this is 500. Okay, right there. But the problem didn't ask for the distance between them. It says at what rate is the distance between them changing. So let's label, how about we label our triangle So how do we label this? Let's call this X, Y, and call this Z. So what formula relates these three sides? The Pythagorean theorem, of course. We have x squared plus y squared equals z squared. So since we're dealing with related rates, we have to differentiate this implicitly with respect to time. If we do that, we have the derivative of x squared is 2x dx dt plus y squared is 2y dy dt. Same story for the z, 2z dz dt. Alright? So one thing you want to note is that the dx dt is the rate of change of distance in the a direction. Dx dt is what? Is the velocity of train A, because that's the rate at which it's moving left and right, east and west, right? And then dy dt, what's moving in the north direction? It's train B, is the velocity of the B train. Okay, so keep that in mind. What we're doing is we're taking a snapshot of the rates of change at t equals 2. Alright, so how does that apply here? At t equals 2, we want to find the rate at which the distance is changing. What is dz dt at t equals 2? That's what we're looking for. So we're going to go ahead and carry out that calculation here. So we're just gonna plug in 2 we're gonna evaluate these functions at 2, evaluate these velocities at 2, and then see what we get here. Okay. All right. Before we do that, one thing you notice that that you can divide everything by 2, the entire function, and here we're told that y is equal to 4, x is equal to 300, or y is 400, x is 300, and z is 500. So let's plug that in, and also reduce everything by 2. So we're going to have x is 300 times dx dt is the velocity of the A train at 2 plus, so let me cancel out the 2 so you see what I'm doing here. The 2's, I divided everything by 2, so cancel, cancel, cancel. Y is, what is y? Y is 400. The y dt is the velocity of the B train. We want to evaluate it at 2 also, equals z is 500. And what is dz dt? Dz dt is what we're looking for, the rate at which the distance between the two trains is changing. Okay, so velocity of A train at t equals 2, how do we find that? You go to the table, look at the table. The velocity at t equals 2 is 100 plus 400 times, what's the velocity of the B train at t equals 2? We don't have a table for that, but we have a function. V of B, velocity of B function, is negative 5t squared plus 60t plus 25. So to find the velocity at t equals 2 of the B train, you just simply plug in 2 into this function right here. If you go ahead and do that calculation, you get 125. So plug that here, you have 400 times 125 equals 500 dz dt. Okay, and then this is simple algebra here. If you do the calculations, you end up with dz dt equals 160 meters per minute. So this is the rate at which the distance between the two trains is changing. Thanks so much for taking the time to watch this presentation. I really appreciate it. Do feel free to subscribe to our channel for updates to other cool math clips such as this. And do visit our website on mathjoseph.com under AP Calc for the remainder of this review series. Thanks again for watching, and have a wonderful day.